Okay, as a continuation to my previous video, I would like to add one more problem where we use the first shifting theorem along with the partial fraction technique. Okay, for this let us look at an example here. Now we would like to calculate the inverse Laplace transform for s by s power 4 plus 4a power 4. This is the example I have chosen. Okay, and this can be initially written as L inverse of s by, see here we can use once again that a plus b whole square type. Okay, so this can be written as s square plus 2a square whole square, where we get s power 4 we get, 4a power 4 we get, and then additionally we get 2ab term. So what is the 2ab? 2 into 2 4a square s square. So this can be also written as 4a square s square can also be written as 2as whole square. So I need to remove that particular term. So that's why I have put a negative sign. Okay, and this can be also written as it is something like a square minus b square form, isn't it? So this can be written as L inverse of s by, now this can be written as a plus b into a minus b. So this is s square plus 2a square plus 2as, right, multiplied with s square plus 2a square minus 2as, which is a plus b into a minus b. So once again we can apply the inverse Laplace transform to this particular function. So, okay, so we have to apply the partial fractions. Okay, we have to apply the partial fractions, and this can be written as 1 by applying the partial fractions. I am writing this directly. This is s square plus 2a square minus 2as, okay, minus 1 by s square plus 2a square plus 2as. So this is obtained by splitting into partial fractions, right? So that I have s square plus 2a square minus 2as into s square plus 2a square plus 2as, and here s square plus 2a square plus 2as, this is minus of, so we'll get 4as. Okay, and s will remain in the numerator, and additionally 4a term will get in the numerator. So to cancel that, I will multiply and divide with 4a. So 1 by 4a times L inverse of this. This is what will remain when I find the inverse Laplace transform. Now how we can simplify this further? 1 by 4a times L inverse of, okay, I am now writing the first term, which is 1 by s minus a whole square, because it is the same as s square minus 2as plus 2 plus a square plus a square. So s minus a whole square plus a square. This is my first term, minus 1 by 4a. Okay, I am writing 1 by 4a for the second term also. Again the L inverse is to be taken here. L inverse of, this is 1 by s plus a whole square, s square plus 2as plus a square. Additionally one more a square is to be taken, okay, to equate the term. S square plus a square plus 2as it is now, right? Now further this is now 1 by 4a. Okay, now see the first term, L inverse of 1 by s minus a whole square plus a square. In that entire term, wherever s is present, it is something like s minus a. So I can apply the first shifting theorem here. L inverse of f bar of s minus a is what? E power at, okay, into f of t. What is f of t? L inverse of f bar of s. That means s minus a should be replaced with s only. So it will be s square plus a square. Okay, minus 1 by 4a. Now what about the next term here? Wherever s is there, s plus a is available for us. So L inverse of f bar of s plus a is what? E power minus at. So e power minus at, L inverse of 1 by s plus a is replaced with s only, s square plus a square. Okay, now I have 1 by 4a, right? E power at, 1 by 4a e power at. L inverse of 1 by s square plus a square is present in both the terms, which is 1 by a into sin at. So e power at minus e power minus at. Okay, 1 by 4a is common anyway for both the terms. We have e power at minus e power minus at. Even L inverse of 1 by s square plus a square is common for both the terms, and its inverse Laplace transform is what? 1 by a into sin at. 1 by a into sine at. And when you look at the exponential function, when you look at the exponential term here, it is something like e to the power of x, okay, e to the power of minus x. E power x minus e power x minus x is 2 sine hx. E power x minus e power minus x is 2 sine hx. So we have at is present in place of x. So 1 by 4a into a is 1 by 4a square. So and as we get sine hx, so this is 1 by 2a square. Okay, sine at I am writing, which is available already there, and hyperbolic function also we are getting over here, 1 by 2a square into sine at into sine h at. This is the final answer. Okay, using the inverse Laplace transforms, we have used the partial fractions technique, and not only that, shifting theorem also we applied. Right. Now, what are the other properties that we have to look into in the inverse Laplace transforms? Okay, so other properties in inverse Laplace transforms. Inverse Laplace transforms. Let us look at some of the other properties in the inverse Laplace transforms. Okay, so the first one that we are talking here is, okay, let us look at the first property. If L inverse of f bar of s equal to f of t, then L inverse of s into f bar of s, L inverse of s into f bar of s is f dash of t. Okay, and this is obtained when f of 0 is equal to 0. F of 0 is equal to 0. So whenever f of 0 is equal to 0 and whenever L inverse of f bar of s is equal to f of t, then L inverse of s into f bar of s is f dash of t. Right? And not only this, if I multiply f bar of s with s to the power of n, L inverse of s power n into f bar of s, this is equal to fn of t. What is fn of t? This is the nth derivative of f of t. Okay, and this exists whenever, that is provided f of 0, okay, f dash of 0, right, f double dash of 0, and so on, fn minus 1 0, all these terms will become 0, then only this is true. And this we have seen in the where we have observed this property we have observed in the Laplace transforms of derivatives. Okay, so when you are trying to find out the inverse Laplace transform, when the given function f bar of s is multiplied with s, then what we have to do? First find the Laplace transform of the given function f bar of s and differentiate it once. If you are multiplying with some s square, first find the Laplace transform of the given inverse Laplace transform of the given function and differentiate it twice, and so on, it continues like that. Okay. Now let us have a look at the next property. If L inverse of f bar of s equal to f of t, if L inverse of f bar of s is equal to f of t, then L inverse of f bar of s by s. So what we are doing here, we are dividing the given function with s. Okay, so this gives integral 0 to t f of t dt. This gives integral 0 to t f of t dt. So this is the Laplace transform of integrals property that we studied in the Laplace transforms. And coming to the inverse Laplace transforms, this is something like in division by s. Okay, division by s. The previous property is something like multiplication by s, and this property is of division by s. So L inverse of f bar of s by s is integral 0 to t f of t dt. Okay, next, if L inverse of f bar of s equal to f of t, now let us see the next property. L inverse of, okay, what I am doing now, f bar dash s, I am now finding the derivative of f bar of s. So this is given by minus t into f of t. Okay, so what we are doing here, first we are finding the inverse Laplace transform for the function f bar of s, which is f of t, and that is just multiplied with t. okay, and this with a negative sign, and this gives the inverse Laplace transform of the derivative of the function. If I have L inverse of f bar double dash of s, right? Now what this is going to give? So we have minus 1 whole square t square f of t, and this continues, and I am now writing the generalized rule L inverse of f bar ns. This is equal to minus 1 whole power n t power n f of t. That means we have f of t multiplied with t power n, isn't it? So this gives the inverse Laplace transform for the nth derivative of the function. Okay. For one more last property we will discuss here. Okay. If L inverse of f bar of s is equal to f of t, then L inverse of integral s to infinity f bar of s ds, this is equal to f of t by t. The same properties you can easily observe that whatever properties we discussed, right, in the Laplace transform, the same properties are just we are rewriting those properties. So we have seen the inverse Laplace transform of multiplication by s, inverse Laplace transform of division by s, okay, inverse Laplace transforms of derivatives, and this is what finally inverse Laplace transforms of integrals. Okay, I think all these properties are very clear. Just go through them once again. Let us see how they are applied to different examples. Okay, now let us have a few examples on some of the important properties that we have discussed so far. Right, now I would like to find out the inverse Laplace transform of 1 by s into s plus a whole cube. Okay, for this I would like to calculate the inverse Laplace transform. So we can use the partial fractions technique to find out the inverse Laplace transform. But once you are thorough with some of the other properties that we discussed just now, we can easily find out the inverse Laplace transform without going to the partial fractions technique. The same problem can be rewritten as L inverse of 1 by s plus a whole cube by s. The same problem can be written as L inverse of 1 by s plus a whole cube by s. It is L inverse of, it is something like now L inverse of f bar of s by s, that is division by s property. So in the division by s property, what we have, what is the property? L inverse of f bar of s by L inverse of f bar of s by s. So in this property what we have, this is integral 0 to t f of t dt. This is what we have. So what is our f of t? F of t is the inverse Laplace transform of f bar of s. So this can be rewritten as integral 0 to t, what is f of t? L inverse of f bar of s. In this particular case, in our problem, what is f bar of s? It is 1 by s plus a whole cube. Okay, 1 by s plus a whole cube into dt. So for this, first we will calculate the inverse Laplace transform, and then that is to be integrated between the limits 0 to t, between 0 to t. Right? Now what is the inverse Laplace transform for 1 by s plus a whole cube? This is integral 0 to t. See here, wherever s is present, s plus a is there. So we have f bar of s plus a form. L inverse of f bar of s plus a is e power minus at into f of t. So this is now e power minus at, s plus a is replaced with s only, L inverse of 1 by s cube into dt. Now this is also same as integral 0 to t e power minus at, what is L inverse of 1 by s to the power of n? It is t to the power of n minus 1 by n minus 1 factorial. So this gives t square by 2 factorial into dt. L inverse of 1 by s to the power of n plus s to the power of n is t power n minus 1 by n minus 1 factorial. Now I would like to do integration by parts, and the limits are to be substituted. and this is now same as, so 1 by 2 factorial, which is 1 by 2. I can bring that outside the integral sign, and now I am taking t square as my u and e power minus at as t. So this gives t square times t square into e power minus at integration is e power minus at by minus a. I am using the Leibniz rule for integration by parts here. T square is my function, which is u, e power minus at by minus a, that is v. So integral uv formula I am using. Now the derivative of t square is 2t, e power minus at by minus a. The integration of e power minus at is minus a. Already minus a is present, so it will be a square. Okay, now I will put a plus sign, so you can observe that alternate minus plus minus plus minus plus we are getting. 2t derivative is 2, and e power minus at integration is e power minus at by a square into minus a, which is minus a cube. Okay, right? The limits are from 0 to t. The limits are from 0 to t. So this is the integration by parts, Leibniz rule for integration by parts. So t square, first I have chosen t square, e power minus at by minus a, and then t square derivative 2t. Whatever I have kept here within the brackets for this particular term, integration is carried out. Next, for this particular term, integration is carried out, and so on it continues. Now this is 1 by 2 times. Now I need to substitute the upper limit. What is the upper limit? T is equal to t itself. So this will be minus t square e power minus at, okay, t square by a, and for this also there is a negative sign, so 2t by a square e power minus at, and for the third term also there is a negative sign, 2 by a cube e power minus at. Now while substituting the lower limit, in place of t, I will put t is equal to 0, so that the first and second terms will get vanished. The first and second terms will get vanished. So only the third term will remain, and for the lower limit there is again a negative sign, so it will be plus, right? So 2 by a cube, because e power 0 is 1. Okay, and this will be our final answer. If there is anything to simplify, we can do that. Otherwise we can keep that as it is. If you want to bring that a cube also outside, this is 1 by 2a cube, right? A cube is drawn outside, right? And this constant I am writing first, so 2, and then a cube is drawn outside, and this will be minus 2 into e to the power of minus at, right? Minus 2 into a into t e to the power of minus at, okay, 2 into e power minus at, 2 into a into t into e power minus at, and then for this term it will be a square into t square into e power minus at. Okay, just you can cross check whether you are getting the same thing or not, right? 2t square, so yeah, okay, a square t square by 2. Okay, so this will be our final answer. Now let me show you one more example using some of these techniques that we have discussed to find out the inverse Laplace transforms. Okay, let us take one more example. Now if you would like to calculate the inverse Laplace transform for, let us say I have tan inverse of 2 by s square. This is the given function. So for this I would like to calculate the inverse Laplace transform, but there is no technique, there is no direct formula to find out the inverse Laplace transform for tan inverse. So let us assume this is my f bar of s, because anyway inverse Laplace transform is applied to a function of s. So my f bar of s is tan inverse of 2 by s square. Now what I will do is, whenever we have problems based on the tan inverse, cot inverse, logarithm, if these type of problems are all given, make sure that you are applying the what is that property, Laplace transforms of derivatives of the inverse Laplace transforms of derivatives, f bar dash s, f bar double dash s, and so on. So for tan inverse, cot inverse, logarithm, for all these type of problems, inverse Laplace transforms of derivatives is applicable. Okay, now for this what I will do is, I will find f bar dash s. I am now finding the inverse Laplace transform of derivative of the function first. With that I can easily find out what is the inverse Laplace transform for the given function. So for that I have chosen f bar of s, and now I need to calculate the derivative. Tan inverse x derivative is 1 by 1 plus x square. So I have 1 by 1 plus 2 by s square derivative is 4 by s to the power of 4. 4 by s to the power of 4, and 1 by 1 plus 2 by s square whole square, which is 4 by, and 2 by s square derivative is what? That is 2 into minus 2, which is minus 4. So minus 4 by s cube into minus 4 by s cube. And this is also same as, I can take LCM as s power 4 in the denominator, you can cancel with s cube, and we'll be left with one more s in the numerator. So minus 4 by s power 4 plus 4. Minus 4 by s power 4 plus 4. Okay. Now what I did so far, just I have calculated the inverse Laplace transform. Just I have calculated the derivative of the function f bar dash s. Okay. Now let us apply the rule. So what is the property? By the property of inverse Laplace transforms of derivatives. Okay, by the property of inverse Laplace transforms of derivatives. Now what I am having, let us write the property L inverse of f bar dash s. L inverse of f bar dash s. This is equal to, what is the property that we discussed? This is minus t into f of t. Minus t into f of t. Okay, this implies, now what I need finally, I need f of t, that's it, because I need to calculate the inverse Laplace transform for my f bar of s. This implies what is my f of t? I'll bring this t to the left side, cross multiplication, this gives minus 1 by t, L inverse of f bar dash s. L inverse of f bar dash s. Okay, now I'll just substitute whatever I got for this f bar dash s. So this is same as minus 1 by t, okay, L inverse of, what is my f bar dash s? Minus 4s by s to the power of 4 plus 4. L inverse of minus 4s by s to the power of 4 plus 4. Okay, now this is equal to 1 by t, because you can take out the minus, it will be plus, minus minus, L inverse of 4s by s to the power of 4. So L inverse of 4s by, and how will you write this? Again you can bring this into the a plus b whole square form, right? So this will be s square plus 2 whole square. This will be s power 4 plus 4, and then 2ab term is 4s square, and we can write that as minus 2s whole square. Minus 2s whole square, right? And it is something like a square minus b square, which is a plus b into a minus b. So this will be 1 by t times, okay, L inverse of, and then I can even apply the partial fractions again for this to split this into two terms. S square plus 2s plus 2, right? This is a plus b, and then s square minus 2s plus 2, a plus b into a minus b, right? And this is same as 1 by t times, and splitting this into partial fractions, what I'll get? 1 by s square minus 2s plus 2. Okay, and a similar problem we did in our previous video, right? 1 by s square plus 2s plus 2. Right, now the inverse transform is applied separately for both the terms. So this is same as 1 by t times L inverse of 1 by s minus 1 whole square plus 1, s square minus 2s plus 1 plus 1, and then what is the other term? This is s plus 1 whole square plus 1, and this leads to what? 1 by t times, and then here the shifting property again comes into the picture. First shifting theorem, this is e power t times L inverse of 1 by s square plus 1, right, minus, what about the second term? E power minus t L inverse of 1 by s square plus 1. Okay, and 1 by t is common for both. 1 by t is common for both. And this gives our answer. So 1 by t times e power t minus e power minus t L inverse of 1 by s square plus 1 is the same for both, and 1 by s square plus a square inverse transform is 1 by a sin a t. So it is sin t, and e power t minus e power minus t is 2 sin ht. So this is 1 by t sin t, right? Already it is there, sin ht, 2 sin ht. So this will be 2. So 2 by t sin ht, and this will be our final answer. And hope you understood the concept, and we will cover up more things, few more things in our next video.